All right, so what we're going to do here, I hope, is discuss acids and bases. And to start that off, I first have to make sure you understand the process of equilibrium. And equilibrium is basically a state where there's a ratio between one form and another. So at school, during the school day, there's a number of kids in the school, there's a few kids out of the school, and there's an equilibrium that's established. The numbers don't change, but the kids change, right? So kids come late to school because they were running behind or they were trying to miss a test or whatever. And then kids leave school because they have an appointment. But the ratio of kids in school and out of school kind of remains the same. So while one person may come back from the orthodontist, another person might leave for a spray tan. And that is how it goes. Then an event will occur that'll change the equilibrium. So this equilibrium is sort of established where there's, this percent out and those percent in. And then after school, there's an event, right, after school where it changes, where a bunch of kids go home. Some kids stay behind because they're in sports or in theater or whatever, and they have practices and rehearsals and extracurriculars. But again, some people will come because they forgot their homework, and some people will leave because their parents are picking them up. And that's sort of what equilibrium is that the ratio stays the same, even though the individual pieces may not be the same. And just as this case, there's really a one-sided equilibrium. There's a more equal equilibrium. If you keep track of my cat here seen almost sleeping because God forbid he actually do anything you want him to. And as I'm walking through the house, I'm just keeping track of, is he asleep? Is he awake? And you will see that pretty much it's a 50-50 situation. If he's not running around, he's sleeping. And that can happen as well with chemicals, where some chemicals are in a very much 80-20 situation, and some chemicals are more in a 50-50 situation where they're kind of here and they're kind of there. And the difference between these two has to do, so chemical equilibrium is when both reactants and products are present in amounts or concentrations that stay consistent with time. And the crux of all this, the reason this is happening, has to do with activation energy. So here we can see that certain things, this is going to maintain a certain ratio, although apparently not great, but there you go. All right. So this will maintain sort of a same ratio. It's not the same things that are staying over here and the same things that are staying over there. But because the activation energy is so low for something to become a product and so high for a product to go back to be a reactant, the ratio stays pretty much one-sided where you have more products and reactants. If we were in a 50-50 situation, then they would be closer to each other where they can go back and forth pretty easily. And then you would have more 50-50 situations. So the activation energy horribly demonstrated right there by 13-1. But hopefully this gets to a point where it makes sense that everything would be equal-ish, because it's not that hard to go back and forth. And that is what creates this equilibrium of a 50-50 situation. All right. So now that you understand that, and we say that equilibrium is reached when the forward reaction and the backwards reaction are happening at the same rate. And that's important because when we learn about acids, and a very fundamentally sound definition of an acid is that an acid produces H plus in water, right? So here's H plus, and a base produces OH minus in water. So here's your H plus. That's HCl is an acid because it produces H plus, and NaOH is a base because it produces OH minus in water. And that works really well for many levels of understanding what acids and bases are. And as we discussed, leading H's are a key to acids because since they give that up and the acid's kind of acting like a metal, the hydrogen's acting as a metal with a positive charge, that's why it's in front, as metals usually are for ionic compounds. That is how you can tell an acid when you're looking at it. Plus the names have the names like sulfuric acid and hydrocyanic acid or whatever they are. Anyway, all right. I will sometimes say H plus is a proton because if hydrogen is a proton and electron, and to become H plus, you need to lose the electron. what's left is the proton. So H plus and a proton are basically the same thing. So this acid here is producing H plus, which is a proton. Right? Why are these important? One reason they're important is they get together and make water, and you should know this. If you are lucky to go to a school where they do this, I will never do this, but you can take concentrated acid in a certain amount and, dissolve metal in front of everybody to see how that is. And then you can take concentrated base in some amount and dissolve hair, or, turn your skin to soap or whatever in that. And then you mix them in the perfect amount so that every H plus reacts with every OH minus and nothing is left behind. All that'll be left is water, and you can drink the water. The problem is if you over or underdid one, you would have left over one or the other, and then it's not water. It's either the base that you had left over or the acid that you had left over, and that's bad news. So acids and bases react with each other to form water. The other things that aren't doing anything, the sodiums and the chlorides and whatnot that you see here, or the sulfates or whatever it is, that aren't involved in any real reaction, we call spectator ions. And like Perry the platypus, they don't do much. So here are some acids. Acids will have that formula with a leading H. That's how you know they're acids. The H is letting you know that hydrogen is coming out, acting like a metal with a positive charge. The anion charge will dictate how many H pluses you can have. So here, Cl being in group 7 has a -1 charge. So the H has to have, with a +1, there'll be a 1-to-1 ratio of hydrogen to chloride. HBr is the same way. H2SO4, you may remember sulfuric acid, SO4 has a -2 from the polyatomic ion chart, so it can handle 2 pluses from the H. PO4 is phosphate, so this is phosphoric acid, that has a -3 charge, phosphate does, so it can handle, look at that, 3. Woo-hoo! So that can handle 3 hydrogens, 3 H pluses to make that neutral. Weak acids are the acids that do more like buzz, where they kind of go 50-50. They don't go one direction. Acetic acid, the acetate anion is a -1 charge, so it can handle 1 H. Citric acid, ascorbic acid, vitamin C, formic acid, what fire ants have and injecting you when they bite you. These are all weak acids. You know that you can eat, right? Vitamin C and citric acid and vinegar. So they're obviously not that strong. They're not going to do that much damage to you. And the reason they're not that strong goes back to the equilibrium situation, wherein not that one, hold on a second, this one, all right, where water has H's and OH's in it naturally, and a strong acid will have a whole lot of those H pluses here signified by H3O plus. So we'll talk about that in a minute. Whereas the weak acids have some H pluses still stuck to the acid, as you can see here in gray, and some are red and go all the way to H3O plus, add that plus to the water. So going back to this, weak bases, weak acids, that's all the same thing. Strong bases is the same thing in regards of it's an equilibrium. Strong bases are very much a one-sided reaction going all the way to just spitting out that OH. Weak bases are amines, things with nitrogen in them, and they sort of do the back and forth thing. And one thing you'll need to know, and it should be pretty obvious, is how to identify an acid or a base. If you know that bases have OH in them, then you know that this is a base, right? Because it has an OH in it. And if acids always have a leading H, then you know that's an acid. So you can see here that nitrogen, not a leading H, that would be a base. That's a weak base, in fact, because it has a nitrogen. Nitrogen, again, is a base. Calcium hydroxide, you're looking at that OH now, that's basic, so that's a base. And then over here, hopefully I did some acids. Nope, I still didn't. Lithium hydroxide, that's a base. H3O plus, H3PO4 rather, phosphoric acid, starts with hydrogen, so you know that's an acid. HCN starts with a hydrogen, so you know that's an acid, has that leading hydrogen acting like a metal coming off with a positive charge. And then NH4OH, the nitrogen, the OH are both telling you that's a base. And HC2, that's acetic acid, has a leading H, so that's an acid. All right, so that is how you identify those. Weak acids and strong acids, as we discussed. The weak acids have sort of this pacifier that Maggie's holding. If that were the H plus, strong acids would hand it to you happily, make sure you have it. Weak acids, on the other hand, while they have an H plus, like acetic acid has an H plus, doesn't give it to you as easily. And so again, going back to this thing, going back to this picture here, a strong acid, right, is giving up that, here's the H plus, the little blip here, is going to water. It's giving up that H plus, and as you can see in this magnifying glass, there are no gray HAs anymore because it's a one-way reaction. It very easily gives up that H plus. Weak acids, on the other hand, here's that H, right? You still see some, it's not sure it wants to give away that H plus and make the red H3O plus. So weak acids are not doing that. Weak bases, the same thing. Here's the base. They are existent in water when they're weak. When they're strong, you can see there's very little of this MOH. There is a lot of OH minus though. So a weak base will create some, weak base will create some OH minuses, but isn't so sure it wants to do it. Strong base is very certain it wants to make that OH happen. All right, I think I'm done talking. All right, so equilibrium is what it's all about. If you have a sort of 95 to 5 ratio, that's what a strong acid would be. If you have sort of a 50-50 mixture where it's not sure it wants to give you that H plus that corrodes things and makes things happen for acids, then that's going to be a weak acid. And the same argument can be made for bases. Now, the last thing is this Bronsted Lowry. They said, I think it's two people, they said that an acid can't really exist as H plus. A proton in any existence is going to be surrounded by a bunch of negative things. So they said it's more accurate than in water. It's H3O plus because that H plus is going to sort of hover around here by this lone pair of electrons and form H3O plus. Whereas a base is a proton acceptor. The reason it's a base, the OH or even the amines, is because they have a lone pair available and the H comes and gloms on there. Same would be true for, if you think about what OH minus is. If you think about what OH minus is, right? OH minus is going to have two lone pair, three lone pair. Yeah, it's going to have three lone pair. So that positive hydrogen can come glom on near one of those lone pair and sort of, be a vagrant there and hang out. All right, so that is that. I hope that helps. And I am now going to stop this video. Thanks for watching.